Hey everybody, it's Ripley back again. We're going to talk today about parametric curve. Now, parametric curves, what exactly is that? Well, we know that we can graph a function, right? If I've got x and f of x, then I know that I can graph a function like that, right? We know it's a function because if you hand me an x, I only give you at most one f of x or y back to you, right? We know that we can also kind of steal, like if I have a circle, which clearly isn't a function because it doesn't pass the vertical line test, but I can still, let's say that this is x squared plus y squared equals a squared. I can actually sort of, excuse me, I can actually sort of cheat and say, well, I'm going to take the top half of the circle, which would be y equals the positive square root of a squared minus x squared, or maybe I'll take the bottom half of the circle, right? In which case, this guy down here, y would equal negative square root of a squared minus x squared, right? So that's an easy way to sort of turn a not function into a function. There's a bit of a problem though. What if I have a curve that does something like this, right? Like a bug crawling across a table. Excuse me. Now we're in big trouble because what ends up happening is, like, what am I going to do? Am I going to bust this thing up into, okay, that kind of looks like a curve, and then that, or kind of looks like a function, and then I can grab this little way, and that it doesn't work. So what we do with parametric curves is excuse me, I'm dying here. What we do with parametric curves is we actually create additional structure. And with the additional structure, what we do is we set t as a parameter. Now, we can let any variable be a parameter, but it kind of makes sense that we would let t, kind of like time, be the parameter. So t is parameter, right? And parameter. And then, so this, we would take an initial point, right? So this would be t equals 0, which would be our initial point. And then along comes our creepy crawly whatever bug. And then this could be at like t equals 1, and this guy would be at t equals 2, and then this guy right here would be at t equals 3, and then this would be our terminal point, right? At t equals terminal. Now, you may say, wait, why would I want to do something as awful as this? Well, because it allows us to describe curves without having to have them be functions. And they don't, truthfully, they don't even really have to be like curves that we know about. Like, we can parameterize pretty much whatever we want. We can even parameterize functions. Now, the way that a parameterization works is, what we have is we have an x of t and we have a y of t. So in this case over here, in this example, this point is still on the Cartesian plane. It just has the point x of 1, comma, y of 1. And there's this additional parameter, this t parameter, think of it as time, as sort of floating over the curve itself. I take t equals 1, I shove it into this x of t and y of t, producing an x of 1 and y of 1, and that's where I stop. This point would correspond to x of 0, x of 0, and y of 0. We played around with these in pre-calculus. You saw them, but we're going to get a little more tricky, and I'm going to show you how to use your calculators a little bit better, and I'm going to show you a couple of tricks here. All right, so for example, let's figure out what x of t equals cosine of t and y of t equals sine of t would look like. So just for giggles, all right, I've got this guy right here, x of t equals cos of t. Excuse me. What's that going to be? So typically, when we're talking about the trigonometric functions, we know that t is going to be wedged between 0 and 2 pi, although it doesn't have to be. All right, it might just be like t is between 0 and 7, or t is between 1 and 3, something like that. And we'll putz around with those when we look at it with our calculators. So again, this should be review, so I don't mean to bore you, but let's take a gander anyway. I'm going to call this one, what is that one? 1, 2, 3, 4. Call that one 1, 2, 3, 4. That one 1, 2, 3, 4. Okay, cool. So when t equals 0, we know that cosine of 0 is 1 and sine of 0 is 0. So we're there. All right, when t equals pi halves, we know cos is 0, and sine is 1. So that gets me up there. When t equals pi, we know that cos is -1, so x is -1, and y is 0. So boom, right here. And then when t equals 3 pi halves, I know that cosine is -1, so x would be when t equals 3 pi halves, cosine is 0, and sine is -1. So that's down here. So what we get, again as a review, is we get a circle of radius 1. Terribly drawn. So good Lord, what just went wrong in my life? We're talking about a circle of radius 1. Now, one thing that's really important about parameterization is where we start. So let's change colors. So where we start, this is my initial point, and then the direction that we go. We carve this guy out this way, like that. All right. Now, hopefully you see that if I went from 0 to 7, what I would get is I would get a little bit more of the function, wouldn't I? Because 2 pi is about 6.28. 7's bigger than that. So I would go once around the circle and then once more a little bit. All right. So what we carve out completely depends on our domain of our parameter, which in this case again is t. Now what would happen, I'm not going to get too crazy here, but I'm going to cheat a little bit. Let's use purple. If I did x of t equals sine of t and y of t equal cosine of t. Well, should be obvious, instead of starting at 1, 0, when t, again, t between 0 and 2 pi, when t is 0, sine is 0, and cos is 1. So I would start here, wouldn't I? When t is pi, sine is 1, which means x is 1, and cos is 0. So now what I'm doing is I'm carving out the same terribly drawn circle, but I'm doing it in the clockwise direction, which is kind of cool. Now, there's one other ramification. We're going to explore this on the calculator. I got the calculator down here so we can pop it out really quickly. What would happen? Whoa, go away. What would happen if I wanted to move this circle over 1? All right. Now, remember, if I wanted to move a function over 1, I had to do like, okay, f of x, like square root of x. I had to remember that it was f of x is equal to the square root of x minus 1, right? I had to put that -1 in there because it moves opposite its sign when it's composed inside the function. Parameterization, you don't have to worry about that, man. Think about it. If I want to move this thing over 1 and down 3, I simply add 1 to all of my x values. Whoop, it moves it over 1. And I subtract 3 from all of my y values, which is awesome. I'll prove it. Watch. All right, so first things first, whoa. We're going to hit set and quit. I don't know what's going on there. Let's get ourselves acquainted with parameterization. First things first, I go to y equals. Now, I have set my mode to parameterization right there. Okay? Go back to y equals. Let's look at our window. Our window is, by default, 0 to 6.2831853, which is approximately 0 to 2 pi. X and y are both -10 to 10, -10 to 10. Our scale is 1. Hopefully you remember what that is. That just means the distance between the little hash marks. And then my step for t is 0.13. If I want a bigger step, if I want it to be more clanky, I'll show you what that means. We can tweak this t step. All right, so let's go back to y equals. What was the first one that I did? I believe I did cosine of t. It's kind of nice that they fill that in for you. And then sine of t. Again, kind of nice. And then we're going to graph it. There's our circle. Oh man, that's not a very good circle. It's hard to see. So I'm going to tweak my window. So I know that this is a circle of radius 1, so I can cruise down to my mins and my maxes, make this a -2 to 2. And then I can cruise down and go -2 to 2. And then let's graph it. It'll be a little bit prettier. Nice. I can also do zoom square because this thing looks elliptical. So I can go to zoom and square, which is 5. And look at that. Isn't that a pretty old circle? Now, I made promises. I said that I can move this circle over to the 1, or over to the right 1 and down 3 simply by tweaking the equations. Now, I'm going to have to add parentheses, unfortunately, here. So we'll throw in a paren, and I'm going to go +1. And let's graph it and see what happens. Bam! That's pretty cool. And then if I want to move it down 3, I just go, let's see, down here, and I cruise over here, and I end my paren, and -3. I better tweak my window, huh? So let's go back to zoom standard and see what happens, which is zoom 6. Bam. And there it is. Move down 3. which is kind of cool. Okay, now, remember, I made a mighty bold claim. I said that any function could be written as a parametric function. Like, let's change the color of that, shall we? Like, for example, bam, f of x, let's just do equals the square root of x. All right, it's real simple. This is true if and only if x of t equals t. In other words, wherever c and x is, think of t. And y of t equals the square root of t. Now, let me prove it to you. Now, this is easy. Do you not agree that t is equal to x? So wherever I see a t, I can put an x. So y equals the square root of x. T equals x. So this would be y of x equals the square root of x. Now, you got to be careful here, though. Remember, there are limits on this t. This, by default, your calculator throws this between 0 and 2 pi. So when we carve it, we're only going to get for t between 0 and 2 pi. Let's see what that looks like. Excuse me. Let's go y equals. I'm going to hit clear and t. And then I'm going to hit second square root of t. Oh, I got to get rid of some stuff, don't I? Delete, delete, delete. Sorry about that, you guys. And we'll graph it. Whoops, shoot. It's got a 3. I'm an idiot. Let's go y equals. Let's get rid of that 3 because I just did 3 root t, which is why it looks so goofy. And delete. And then let's graph. Well, bam, there it goes. And it stops right there because it only went as far as the square root of 2 pi. Now, if I want to carve out the whole thing, then I would have to put t between 0 and infinity, which I can't really do on my calculator, but I can tweak it just a little bit. So that's really simple. Now, let's reverse it. Let's say that I said that x of t equal, this is where it gets kind of fun. How about I said that this was 3 cosine of t, and I said that y of t equaled 5 sine of t. And I wanted to figure out what this thing was in rectangular form. So there's parametric, they're both rectangular. Let's be careful. In function and or relation form. Well, hopefully, again, I don't want to bore you, but hopefully you remember that you can actually solve this pretty neatly. I would get x over 3 equals cosine of t, and y over 5 is equal to sine of t. If I square everything, I get x squared ninths equals cos squared t, and y squared 25ths equals sine squared t. And if I add those, I would get x squared ninths plus y squared 25ths is equal to 1. Hey, wait a sec, that's an ellipse. Whoops, that's an ellipse, right? We know that it's going to have a major axis along the y-axis. It's going to be 10 long, 5 up, 5 down. It's going to have a minor axis of 6, 3 left, 3 right. Let's graph it. Just make sure that I'm not lying to you. Let's go y equals. I'm going to clear that one out. What I say? I said 3, right? You agree? I think I did. I said 3 cos t, so 3 cos t. And then this one was 5 sine t. And let's see if I can make good on my promises. We're going to graph it. Whoa, whoa. That kind of looks circular. But you know why it looks circular? Because of the aspect ratio of the screen. So let's go zoom. And let's go zoom square and watch what happens. 5. Booyah. There's our nice, it's weird that it looked like a squared circle, and then when I hit zoom square, it turned into never mind, I'm an idiot. Okay, now one skill that's really going to be important for you guys, excuse me, in when you hit Calc 3 is actually, believe it or not, being able to write a line or a line segment in parametric. It's one of the basics, and it's one of the very first things that we do because we can talk about vectors that way. All right, line segment, think of a line segment as being kind of like a vector, or a vector being like a line segment with an initial point and a terminal point. All right, so let's say that we have let's take a point, we'll go 1, -3, and I want the line segment from 1, -3 to -4, 5. Okay? Now the easiest way to do this, let me show you how this works. It's real simple. Is set t between 0 and 1. You can set it wherever you like, but it's most easy if you parameterize between 0 and 1. Now, x of t and y of t, once you've got it in this mode, are super simple to figure out. Think of it almost like a line. I need to start at 1 and I need to finish at -4 after t equals 1, right? So at 0, I want x to be 1. At 1, I want it to be -4. Well, how do I get from 1 to -4? I subtract 5, and I get my t. Now you're like, wait, what? What? Well, look close. When t equals 0, x is 1. Pow! When t equals 1, x is -4. Well, bam! So you can probably see that this is going to be -3, and then I got to get from -3 to 5, so that's going to be plus 8t. And that is going to be a line segment from 1, -3 to -4, 5. And that's super helpful. Like I said, we're going to use this over and over and over again when we start talking about vectors. All right, let's see, what else am I missing? There's like ballistic motion or rectilinear motion. Do you remember those guys? We'll play around with those just a little bit. Let's see if I can remember what these were. Remember, if I launch a projectile motion is another way to say it. Like if I throw a football, right, with an initial height of h naught and an angle to the horizontal of theta. Remember, x of t is equal to, and with an initial velocity, of course, is equal to v naught of cosine theta times t. Remember that? That was from pre-calculus. And y of t is 1/2 v naught t squared. That's starting to smell a little bit like antiderivatives, right? That's the drag, or let's see, that's going to be a negative, isn't it? Negative, because the acceleration is negative on it, plus v naught sine theta t, and then plus h naught. Remember that? So think about this. This is the v naught cos theta is the horizontal component of the v naught, and then times time. So that's going to give me the horizontal distance that it travels. The vertical component is going to be v naught sine theta t. That's the vertical component of the initial velocity. H naught is the place from whence it was thrown, and then -1/2 v naught t squared is the negative effect of gravity on the ball being thrown up. So again, that's projectile motion. You've seen all these things before. I think you'll really enjoy it. The coolest part, really, truthfully, honestly, is this component, is this aspect. We can move stuff around. It's really, really easy to tweak these equations to behave very nicely. You're going to do a lot of graph matching in here, which I think is really cool. I would recommend you can just pop open your calculator and throw some graphs in there. Like if you want to, let's find it just a god-awful monstrosity. Let's do this one. This one's fun. You know me, I like my god-awful monstrosities. Clear. If I do, let's do x of t equals sine t minus sine of 2t. Oops, I need to stick another parenthesis in there. Bear with me, guys. So second insert. The lag on this can be very disorienting. Okay, so we're good there. And then let's just go cos t down here. So clear cos t. Okay, now let's take a look at the graph first. Make sure all my, let's see, what's my zoom? I think I hit zoom square, didn't I? And then we're good there. Let's graph this thing and see what happened. Whoa, I need to zoom way in. Let's go zoom in to 2. Let's go enter, because I want to see. Wow, look at that. That's pretty cool, man. All right, let's see if we can zoom in more and get even a better, see if we can get it more detailed. Enter, pow. Yeah, that's crap. Let's go zoom out, and that'll give us what we need. Zoom out, enter. Man, that's pretty neat. Now, let's look at this thing. It's kind of like a weird hourglass shape, but let's take a gander in terms of why it does what it does, okay? So look close. It appears as though the biggest that x can get is about -2 and about +2. And the biggest that, the most extreme, not the biggest, the most extreme that x appears to be wedged between -2 and 2, or somewhere around there. Y appears to be wedged between -1 and 1, doesn't it? Well, go back and look at the equation. Let's see, this is sine t minus sine of 2t. It makes sense that y would be wedged between -1 and 1 because cosine, its range is between -1 and 1. Now what we're getting is the interaction, to get that crazy behavior, is the interaction between sine t and negative sine of 2t, right? Is this guy sometimes is going to be positive when this guy's negative, so you get a subtracting aspect. Sometimes they're both going to be positive, or sorry, if this guy's positive and this guy's negative, then I add. If this guy's positive and this guy's positive, then depending on their sizes, I'm either going to get a positive or a negative number. And then because they're both sines and cosines, they cycle through. You end up with periodicity, or a periodic aspect to what goes on. And it appears as though it appears as though this thing repeats itself rather nicely. And once it repeats itself, man, I'd sure love to know what those things are. Well, I'm not going to bore you guys. I'll let you play with it. Excuse me. After it's repeated itself, some pretty interesting things. After it's gone through one entire cycle, then it simply repeats itself and does it over and over again. Now, let's see what the period of this thing is, just real quick, and then I'm done. I'll let you guys be done. Let's change the period from 2 pi to just pi, and let's see if we carve out half of it. See what happens. Yep, sure enough. So the periodicity of this graph is, well, as you guessed it, it's going to be 2 pi. So if I go back to my window and I set this thing to, let's go 2 pi, I get the whole thing again. Now, again, you may ask me, Ripley, what happens if I have more than 2 pi? Well, that's where you can get pretty tricky, and that becomes really important in some of the stuff that we're going to do, particularly in Calc 3, is if I carve out too much of this curve, I won't be able to see it on the grapher, which is kind of a drag. Oh, let me show you one other thing. I lied. I'm not going to let you go yet. Watch what happens here if I do this is kind of funny. If I let my t-step go to like 0.8, watch what happens to the graph. Now, see if you can see if you can predict what's going to happen if I let my t-step get bigger. Remember, you lose resolution, right? If my t-step is too small, it takes the calculator forever to graph it out through the pixels. But if I make it too big, watch what happens. Right? It's like a poorly drawn 4-year-old stick figure of the function. But Ripley, it didn't make it back around. Yeah, it didn't make it back around because our t-step was too big, right? In other words, it started at 0, and then it went to 0.8, and then it went to 1.6, and then it went to 2.4, et cetera, and then this is as close as it got to 2 pi. All right, that's enough of me yapping at you guys today. Hopefully that was helpful. I love parametrics, and they become super important in Calc 3. So don't just sort of glibly go through this section, or you're going to suffer at your own hands down the road. All right, thanks for your time and attention. Have an absolutely wonderful day, and I'll talk to you soon.